So, hello everyone. My name is Denis, and I'm a PhD student at EPFL. I work on Scala. I do research on Scala. And today I would like to talk to you about off-heap memory. And so, what's an off-heap memory? Off-heap memory is a term often used for managed languages, which describes some particular chunks and allocations which do not fit into common GC paradigm. So they're commonly not garbage collected, so you're very often required to do some bookkeeping yourself. So in C and C++, there is no such thing as off-heap memory because effectively everything is off-heap memory, so there's a parallel. So why would you want to do something like this? Like, isn't GC the best possible memory management paradigm ever? Like, doesn't it cover everything? In theory, yes, it does look like it, but in practice, very often when you hit a wall of tens of gigabytes of allocated memory, suddenly GC, especially JVM GC, starts to struggle. And the most common example of struggle is pause times. So it might be pretty good on average, but in some particular moments of time, it can take a few second pause. And for many apps, this is not acceptable. So, for example, if you're doing some latency critical work where you would expect your HTTP request to finish at most in half a second, and suddenly some of your requests take seconds, that's a bit inconsistent. Another use case is, let's say you would like to share a memory between JVM side and native side. So right now, interop requires you copying stuff over and over. If you were to just allocate it at one place and have the API that can access it from both places, that would be nice. So what's the state of off-heap memory right now? So what do people use today on JVM to do off-heap memory? So the most common example is direct byte buffers. Direct byte buffers represent this untyped sequence of byte API where you can put and get stuff at arbitrary places. So it's like an array of bytes, but only optimized for serialization. So it's not very good for everything else. As you can see, API is not very nice. So, and very often it's used for use cases where you put stuff in an offline storage, and then when you'd like to process them, you recover GC objects again. So some limitations of this approach are low-level API, at most 2 gigabytes per one allocated buffer, and also bound checking can be a problem in some use cases, and you cannot turn it off. Another example, which is much lower level, SunMISC and safe. SunMISC and safe is something that is used to implement byte buffers. It's an internal API in JDK, which was actually never expected to be public, but this is actually one of the most common places where people go for raw speed. They just use SunMISC and safe for the use case. For example, Spark recently introduced a new backend implementation of their infrastructure based on it. So in fact, that's what people do most of the time. And this API is actually very, very horrible because with SunMISC and safe, you don't get any safety whatsoever. You, for example, put int unsafe or put int in a second paragraph. If address is not something you allocated, it might actually segfault your JVM. So it's like kind of API that exposes basically a C-level of abstraction. It doesn't care about you, so you will need to do everything yourself. So they said a very low API, no safety, and lastly also memory leaks is also a very real issue with SunMISC and safe, because in SunMISC and safe you allocate memory through direct calls to basically malloc and free, and if you don't call free, you leak memory. Another approach, which is not that often used, but it's also possible, is to write your off-heap stuff in C, and it's actually very problematic because Java doesn't have a nice C interop story. So GNI is an API to make it possible, but it doesn't make it nice. So if you want to do anything non-trivial, you likely drown in boilerplate, and it's like worst of both Java and C like combined together. So issues with this approach are very much the same, only that it's more boilerplate, harder to understand, harder API, and so on and so forth. And also code distribution is complicated because once you have native extensions, you need to precompile these extensions for each and every combination of hardware architecture and underlying platform that you have, that you care about. So it really complicates stuff a lot. So all in all, state of off-heap memory right now is that you don't have much abstractions. You either use byte buffers, which are safe and doesn't provide you any tools to like sort of deal with memory inside of a byte buffer. You can only deal with it as a whole. If you go for any other approaches, you will likely face manual memory management, which is very error-prone. And lastly, all of it is very low-level and very hard to work with. So to address all of it, Scala off-heap was developed. A main idea of Scala off-heap is to provide you data layout primitives, provide you a semi-automatic memory management, and also make it all reasonably high level. But when I say reasonably high level, it doesn't mean abstract everything away so that you cannot access to underground platform anymore, like JVM does. But do it in a way that doesn't really stand in your way. So if you really want to call malloc free, we will not stop you, but we will advise you to use better alternatives. Okay, so let's start with data layout. Data layout is something that is completely missing from a byte buffers API. So the first part of data layout story is off-heap classes. These are classes which are allocated off-heap and can only be allocated off-heap. They're lightweight, they don't have much overhead. So in C terms, you can think of it as a pointer to struct. So that's kind of overhead that off-heap classes have. To define an off-heap class, you need to use one of our annotations. The first one is addData. addData is something very, very close to case class. It has an API which is also very, very close. So you get all of the nice stuff that you're used to in case classes, like nice accessors, pattern matching, a copy and write, helper, nice to string, and so on and so forth. So you can really think of it as an off-heap case class that really does it best to sort of hide away all the scary stuff from you. Okay, so now let's look at data layout part. As I said before, off-heap class is effectively a typed pointer to struct. That's it. It doesn't have any headers that are required for GC. It doesn't have anything else. So if you have a data class with 2 fields, you will just store 2 fields in memory. Appropriate padding might be required so that all of the fields are aligned by the size of their type, but that's it. So apart from padding, you do not get any overhead here. Okay, so now let's see what happens when you compose off-heap classes. As you would expect in Scala and Java, when you compose classes, you sort of increase number of errors. So you, if you delegate and not inherit. And number of errors isn't something very nice because every time you follow an arrow, you dereference and you access the memory controller, and that's slow. So it's not as fast as arithmetic, and it can actually introduce non-trivial latency for your computation. Sort of address this issue, we added support for new magic embed fields. Embed fields let you treat a field like if it's an actual struct. So not a pointer to a struct, but just a struct. So when you say embed start point in a class segment, you really say inline point as a data layout concept into me. And it means that in the end of the day, a segment is actually a nice typed API for ints. So it has the same overhead as if you would have manually wrote just a class with off-heap class with 4 ints. And that's very nice because whenever you reference, for example, those stars do not need to touch memory anymore. You just compute a new address based on base address. So it's just arithmetic, and arithmetic is pretty fast. Okay, so another variety of off-heap classes called enum classes. They're called enums because they enumerate all of the possible branches. They're tagged unions. So it means that when you have an instance of a figure, for example, you will, under the hood, it means that you allocated one of the three cases that you have. We use this syntax a bit different from Scala syntax because we rely on macro annotations, and that's a kind of approach as you get with macro annotation. It looks a bit different, so you do not need to extend a figure anywhere. It's automatically implied for you. So for enum classes, you also get nice helpers, so you can safely cast in this off-heap hierarchy. These casts are safe, so it will show an exception if you do something wrong. You can also pattern match, and so on and so forth. And you have, of course, you have toString, and the string of data classes inside is affected, so you get a nice fully qualified name that actually tells you what's going on. In terms of data layout, as I said before, enumerations are like tagged unions. This is int at first is a tag that tells you which case of the enumeration it is. And the rest, the size of the rest depends on the case. So you can also embed enumerations, and in that case, it allocates the size of a biggest branch, basically. We also do arrays. Similarly, with off-heap classes, we really try to mimic existing APIs and follow the rule of least price. So we try to have the same kind of helpers like map and for each. In terms of data layout, arrays also follow the ideas that we have right now in Scala. So an array of point is array of references to points. And again, there is an extra arrow we would like to remove, and this is why we also introduced embed arrays. Embed arrays, the only difference is that they include the type inside them. So you do not need to follow any pointers again. So again, until you get to an int, you do not dereference anything. So in terms of C, you can think of it as an array of structs. So it's exactly the same thing. It's only that in Scala, default is by reference and not by value, and that's why we need to annotate places where you do not want reference. So it's like inverse of pointer annotations in C in a way. Okay, so now we've got some data layout tools. So off-heap classes and off-heap arrays. What about memory management? So as I've told you before, we don't really try to just in a new way. So that was one of the goals. So our story for memory management comes in two pieces. So first piece is off-heap.memory. It's a very, very thin abstraction layer over SunMISC and safe. It gives us some safety to re-implement it differently if SunMISC and safe goes away in the future. So we do not require you to use SunMISC and safe in your code. So that's good. And also we have some safety checks which are not provided by SunMISC and safe, but we let you turn all of them. So if performance overhead of those checks is not okay for you, you can turn them off completely. Another part of memory management abstractions is off-heap.allocator. And that's basically a trait that represent something that can allocate and free memory. We both support fully manual allocators like system malloc if you want to use that, but please don't. But if you really need to, you can still do this. But also, we seriously advise you to consider regions. Regions are a special kind of allocator which lets you allocate stuff in a particularly delimited scopes. The scopes are like these region blocks. In this region blocks, you get to allocate anything you want, but as soon as a region ends, all the allocations go away. So instead of micromanaging allocations on allocation by allocation basis, like you would do with malloc and free, instead you only need to manage a region, and it's actually much more simpler because regions often correspond to domain-specific notions. Like you can have a region for HTTP request, you can have a region for a particular processing job. And once this job is done, it's clear that memory that's required for this job is not needed anymore. So unlike malloc and free, they have a very nice correspondent with specific lifetimes in your code. To create an instance of a region, you need this props, probes in scope, and it defines a necessary configuration of a region to be opened. Also, we have optional safety for the dangling pointer arrows, and it's optional because, unfortunately, we couldn't make it performant enough to be turned on by default. It has about 60 to 80% overhead over regular references, but in case you wanted more than performance, then you can enable it by a flag. In future, our goal is to increase the number of safety checks that we have, and we expect this kind of checks to be not necessary in future release, because there's actually a very nice theory behind regions that lets you reason about allocations and when they're freed and so on and so forth. So in the future, once we have maybe a compiler plugin, we'll be able to check this kind of stuff for you statically. It's also possible to have open-ended regions. So you open it and close it maybe sometime in the future. It's very nice if you want to tie it into some particular async situation where you do not quite have a scope that has open-ended, but you know specific points in time when you would like to open and close it. Okay, so we've got some abstractions. What about performance? Like, how expensive are they? So for example, let's have a look at allocation performance. So first, the nicest, tallest part is GC. The second one is regions, and last one is malloc. So as you can see, regions are actually much well optimized than malloc, and malloc is actually horribly slow. So coming from a Java background where allocation is free, it's very different. So in regions, we're able to achieve a very close performance to a GC allocation time, and it's actually very nice. Like if you compare it to malloc, for example. For a typical access of fields, we have slight 10%, about 10% overhead. This overhead amounts to checks that you can turn off. So that's a performance of a safer mode. So if you would like to have a fastest mode, it can be as fast as GC reads and writes. So for arrays, it's also similar. For arrays, we also do a bounce checking. So again, you can turn all of it off. So okay, so now it looks like we are slightly slower on most specs. So what happens when you do a bit larger benchmark? Like, let's say we would like to perform a map on large array, and suddenly we are like much faster. Why is it so? Because we actually inline a lot. So all of our APIs are, as I would say in the next chapter, are macros, and it lets us to optimize a lot of stuff that compiler cannot do for us. For example, arrays are unboxed. Closures that you pass to common accumulators on arrays are automatically inlined for you. So in the end, you completely remove boxing and end up with actually much nicer real-life performance. So what's under the hood? How all it works? So main reason why we can even reach on par, like similar performance to JVM, is because we only use abstractions in Scala, which is zero cost. And these abstractions are macros and value classes, essentially. So almost each and every method in our APIs is a macro, and that's what it is. So let's have a look at a simple expansion of how off-heap classes are expanded. So what happens when you say data class? It actually means a value class over an off-heap address. So address is just a physical address. So you can think of it as a void star. So it's untyped pointer. And point, of course, is a typed pointer here. As every typed API you introduce a new type here, a class point, we pre-generate all the nice APIs we've seen before. We pre-generate accessors, setters, and so on and so forth. And here you can see the use of memory. Memory is this very low-level API that you may use, but it's only meant for the sugaring of macros. So in the end of the day, macros generate a very nice low-level code without much overhead. Okay, so what's about that magic array map? Why is it so much faster? And the simple way is we expanded into a simple while loop. It only does simple reasons writes. It doesn't have any closures. It doesn't have any allocations. Like it doesn't have any off-heap allocations inside. So all you do is read part of memory from one place and put it into another multiplied by 2. And as you can see, the closure we've had before that I have just highlighted is gone. So there is no more indirect calls and so on and so forth. So in the end of the day, the main reason why we are noticeably faster is because we do all of this work automatically for you. You can also write Scala code as if it was Java by doing this kind of stuff manually yourself, but that's not the point, right? Okay, so a possible question you may have, can I try it today? And the answer is yes, you can try it. So right now we publish 0.1 snapshot. We are not quite a 0.1 already, but we are very, very close. So here's a link to a very simple project that illustrates on how to basically depend on Scala off-heap. You just need to drop a few lines into your SBT file and you're good to go. So in future, we would like to improve a lot. One of our planned improvements such as near future is to add support for gmalloc as a baseline allocator. I'm not sure if many of you have heard it, but gmalloc is this new optimized allocator that is also endorsed by Facebook that is actually not as terribly slow as malloc. And so it's a contributor. It's currently being developed by Adam Rosenberger, so he's working on this. And he's our first third-party contributor, so I would like to see more of those ideas happen to life. So if you have any idea and you would say, hey, I would like this feature, and sure, I'll come over and we'll help you to work with us. So in a bit further future, we plan to improve our static analysis tools. So in particular, we plan to guarantee there is no dangling pointers in your code by static analysis. So if you use regions, it means that in the future, we'll be able to either tell you that you have a dangling pointer box or it's okay. And there are actually much more features we plan to do. A comprehensive list is available on our GitHub page, so you can just go there. So to sum up, Scala off-heap is an abstraction over existing status quo that tries to be nice, easy to use, but at the same time, we do not try to tell you what to do. We do not try to teach you life and abstract all of it away from you too much. So if you want low level, you can get it. If you want high level, you can also get it. So that's pretty much up to you. That's what people need in off-heap memory. Okay, thank you. Any questions? Yes.
How much do you rely on specific Scala versions, like experimental with macro annotations, and what's the standard for JVM in Java 9 where you cannot use sunless and safe?
So in Java 9, deterministic and safe is indeed planned to be removed, but right now we can't really comment on that because it's not clear what exactly it does mean, because it's not actually even present right now. So it's also like hidden away. So if they hide it away in different place, we'll like take it. Macros. So we rely on macro annotations, and that's not officially merged in a feature into baseline Scala yet. So as far as I can see over discussions, it's very likely that it will happen sometime in the future, and there hasn't been any like note, like definitive no set to macro annotation, so it's likely that we are safe there, I would say. But for now, we need to use macro paradise until Scala meta happens and Eugen develops like a final stable API. I would say there's only a risk here that we will need to rewrite our code for a Scala meta in the future, I think. Yes? Right.
So, is it, do you plan to solve this somehow? I don't know.
So it was sort of a bit mentioned in the slide. So if you use regions, you see constant time cleanup. This basically means no pauses. So, yes. Yes, so our plan is basically to say the stuff that causes you problem on heap, you move it off heap, and then it's not a problem anymore.
So you need to move all the library like select container?
No, you do not need to. You don't need to move everything. So quite often you have basically like when you profile code for performance, you look for hotspots in terms of execution time, and when you compile code for memory management, you look for objects which like basically trash your GC most. And all you need to do is only like take care of those. So you don't need to rewrite everything. But indeed, there is an issue that like yes, we cannot just magically take existing code and turn it off here. But unfortunately, it's not possible with macros. Yes. So one of the simple use cases that I would really like to use it for, but didn't have time yet, is for compilers where you have lots of long-lived objects which are generated at a very fast speed, like what we have with Scala C now. And for example, trees. Trees are huge, and they have a complex structure, and it takes a while to GC them. And I would really like to experiment in that area and basically see if it's possible to tie, basically say that regions are compiler phases, and then suddenly you don't need to have any GC overhead at all. Because for example, on Scala C, right now, if you launch Scala C with one thread, GC will happily eat like the rest 3 cores on my machine. So that's very much what I see right now, and I want this like all of my 4 cores. So that's my personal itch.
What's the maximum heap sizes that you tested with?
So we've tested, like I have a 16 gig machine. Unfortunately, I haven't tested with larger heaps, but this API is really thin wrapper over native stuff. So like regions are like definitely like constant time in terms of cleanup. It doesn't matter how much you allocate because cleanup of regions is just to read and to write. So it doesn't depend if you allocate 1 gigabyte, 10 gigabytes, 100 gigabytes. It doesn't matter. Like it will matter in terms of runtime because whenever you allocate memory, there is some allocation overhead, of course. But this allocation overhead is constant, like spread out over your execution. So it doesn't matter really how much memory you get. Oh.
Could you tell me a bit more about how regions work? So do they resize dynamically?
Okay, that's a very good question. The question is, do regions resize dynamically? So I had a very complicated slide from San Francisco, and people told me it's very complicated to explain precisely how it works. Maybe I have the image somewhere. Come on. No. It was somewhere around. Okay, so this image from Scala days San Francisco, and this is an overview how regions works. So at topmost layer, you have a system memory, and this a place where we allocate large fat allocations from. So it's configurable, but right now I think it's 1 megabyte. It has changed a bit. So we allocate one fat allocation, like fat allocations, and we pool them. So we don't consistently speak with system allocator. So once we pool the memory, we don't need to speak with it again, actually. Then we split this large chunks into smaller pieces. And these smaller pieces are called pages. And then pool is essentially, and pages are like an intrusive linked list of memory blocks. And then regions are nothing more than a list of pages as it grows dynamically. So because these pages are reasonably big, you actually, most of the time you're in a place where you just increment a pointer. And here you can see, for example, in a left region, you have this line which says how much of the current page is free and how much is taken. And all you need to do is basically and this way it's actually very easy to make a constant, like amortized a constant time performance, because once memory is pooled, the only overhead you have is to basically take page and return page. Because it's linked list and we store both begin and end, basically return, you don't need to traverse the inner side. You just take this like list, like both ends, and you put it back into pool. And so it's effectively a constant time. So it doesn't really depend on the size of a region. And as you can see, they're indeed dynamically growing. So they're dynamically growing in 4K chunks. This 4K and 4M numbers are very configurable. So if you want different numbers, you can get like different numbers. But we profiled and we found that 4K, like it doesn't really get better after 4K. So 4K is a sweet spot in terms of page size for this memory pool based regions. Okay, does that answer your question?
Yes, it does, although I do wonder whether you're not shifting the problem to the pool then. So you use one pool for the entire app?
Yes, so the expected use case is to basically use one pool per app. And if you're really super concurrent, you can have multiple pools, and then you can have a pool per like thread or a group of threads or whatever you decide to do. So it's up to you. So both pools and regions are synchronized. So if you see contentions, you might want to have more than one pool, indeed. So the nice piece of this is that it doesn't really get fragmented in the way that regular malloc and free are fragmented. The main problem when you have a malloc and free like system where you need to be able to free allocations on one per basis, you need to sort of mix and match small allocations and big allocations. And it means that depending on order, you might not be able to do an next allocation if you have too many the spaces between allocations are too small. Here, you allocate stuff continuously in pages. So as long as it fits in a page, you actually get minimum fragmentation. And I think I don't have the numbers. I think we actually improve on fragmentation compared to regular allocations, especially default malloc. Yes?
If I understand correctly, because the allocation actually returns the native address in some box,
Mm-hmm.
would be good for big data, immutable data sets.
Absolutely, yes. So one of the ideas why we use value classes is because we want actually everything unboxed. So in fact, the only if you use just off-heap memory, the only garbage that you make in terms of GC is actual origin objects. Everything else is doesn't really have a boxed representation. So I think indeed one of the apps we would like people to use it for is big data. And so for example, Spark right now already does something very similar, only that they use unsafe directly. They don't they sort of have their own small framework, but it's nowhere near with what we have, I think. So I would really actually hope people use it for big data, yes. Yes?
What are data types that you have inside those data classes aside from heaps? Can you have strings or
Okay.
arrays of points?
So the question is, what data types can you have in off-heap classes? So off-heap classes cannot refer back to GC memory. So all you can refer is primitives, other off-heap classes, arrays of off-heap classes, and whatever else we come up with in our framework. Unfortunately, it's impossible to add support, to have efficient support back to GC objects, because it would mean that GC needs to traverse our memory and know how our memory works to know if GC objects needs to be allocated, and that's not possible unless we do our own GC. So, and we are not going to do our own GC on JVM. Yes?
Would it be possible to share relation across different processes?
So if you use something like memory mapped files, so this address is actually just a physical address in memory. So if you can do it with tools you have in C, you can do it with Scala heap. So you can basically create your own allocator which use memory map, and then you sort of
With no checks.
I'm sorry?
With no checks.
Yeah. Exactly. So row pointers are always valid pointers in Scala heap. We also have, for region pointers, we tag them in a magic way, but we tag them in a way that doesn't disturb native pointers. So native pointers are always correct. So even if you have memory checks turned on, it still works. Yes?
The memory layout is the same as for C structs, right?
So memory layout, so whenever you have a data class point, when you say val x point, it means a pointer to point, not just a structure point.
Yeah, okay, but at the address, I mean, if you want to interoperate with, say, C libraries,
Yes.
construct the analog of C structs.
So an analog is to use basically embed annotations to invert pointers. So you can get very close. So right now we do not guarantee that we will do exactly the same layout as C, because layout as C is not something very well specified. So I think for a simple use cases we'll have exactly the same layout, but I cannot guarantee that we'll have exactly the same layout for complex nested data structures, because I haven't tested it yet. But I think for a simple use case, it's definitely possible to define a data class of heap in Scala of heap and define a struct in C, and then a pointer to the struct will be the same, at least for data structures of primitives, I think, yes. But for a complex, I think it's not clear, we do not guarantee that. But we would like to.
Just to call
Yeah. So foreign C interop is something we are very interested in as a research area in the future. We cannot say anything for sure right now, but that's one of the areas we would like to explore, to basically maybe have a better foreign function interface story for Scala, but it's too early to tell. Yes?
Do you have any plans for support variable length fields inside those structures? For example, embedding an array of primitives.
So right now, our arrays are variable size, and you cannot embed them. You can only embed a fixed size entities. But we plan to introduce fixed size arrays in the near future, and you will be able to embed a fixed size array. So it does this.
Okay, but you could have a structure benefit from memory locality, for example, and have an header, for example, indicating where each field starts or ends. Would it be useful?
So right now, we don't have support for anything like this. But if you're interested and you can and you want to discuss, please come to our issue tracker and just say, I want this, and we can discuss. Any more questions? Okay, thank you.